what's really on the moon Titan. Today, we set course for a hazy, icy world, and one that feels eerily familiar. Nestled in the orbit of Saturn, Titan, the planet's largest moon, conceals a universe of its own. Lakes of liquid methane, hydrocarbon rains, dunes sculpted by the wind, a frozen echo of Earth, but under an orange sky. And beneath its frozen crust, a subterranean ocean might just harbor the conditions for life. Titan is not just a satellite. It's a complete, complex, fascinating world. And what if life there followed an entirely different path than on Earth? But before embarking on a new adventure, remember to like the video and subscribe to the channel so you don't miss anything. Thank you and bon voyage. Our journey begins with the exploration of Saturn, a gas giant over 1 billion kilometers, or 621 million miles from Earth, beyond the asteroid belt and Jupiter. In sixth position from the Sun, it is surrounded by spectacular rings. Located about 1.4 billion kilometers, or 870 million miles from the Sun, it receives much less light and heat than Earth. Its distant orbit makes a Saturnian year last almost 29 Earth years, which slows the cycles of its rings, atmospheric evolution, and the climates of its moons. While Saturn has been observed since ancient times, it was only in the 17th century, thanks to improved telescopes, that it was understood that the protuberance seen around the planet was actually a ring. As we move closer, we distinguish the three main rings, A, B, and C. Composed mainly of fragments of water ice mixed with dust and organic materials, these grains vary from one area to another, ranging from a few centimeters or inches to several meters or feet. The central B ring is the densest and brightest, while the outer A ring is separated from B by the Cassini division, a less dense area. The C ring, closest to Saturn, appears diffuse and less reflective, visually organizing the whole. Scientists believe these rings formed following the fragmentation of an ancient satellite or repeated collisions with comets and asteroids. Their vertical undulations and the gravitational resonances exerted by the moons demonstrate their great dynamic complexity. Continuing our journey, we discover a retinue of about 146 satellites, a number likely to grow with observational advances. Their diversity is remarkable. Mimas and Enceladus bear icy surfaces riddled with craters and fissures, suggesting an underground ocean or geysers. Iapetus presents a striking contrast between a dark face and a very bright one. Irregular satellites, probably captured asteroids, complete this multitude. The interactions between these moons maintain the structure of the rings and create subtle orbital resonances. Among them, Titan dominates, representing nearly 96% of the total mass of Saturn's satellites, making it the main target of our upcoming explorations. Titan, the largest moon of Saturn, is even larger than Mercury. Its substantial mass and unique chemical composition make it a major scientific target. Endowed with a dense atmosphere rich in nitrogen, methane, and organic compounds, it is enveloped by an orange haze that largely masks its surface. The existence of lakes of liquid methane and ethane, immense dunes, and potential cryovolcanic processes generates strong interest in studying the geology and prebiotic chemistry of this world. Historically, Titan was first observed in 1655 by Christian Huygens, marking the discovery of a moon after those of Jupiter. At the time, this discovery reinforced the idea that other bodies could have atmospheres. The Voyager and Cassini probes later revealed Titan's hybrid structure, blending ice and organic materials, illustrating the diversity of the Saturnian system where tiny captured rocks and planetary-sized satellites coexist. In traversing the empire of Saturn, the planet appears as the conductor, guiding the evolution of an armada of celestial bodies, while the rings offer a spectacular stage, fascinating by the complexity of their patterns. The interactions between moons and rings produce a finely tuned gravitational ballet, where every icy particle or large moon influences the formation of divisions and undulations. Titan, by its dominant mass, takes a central position, ready to reveal the secrets of its atmosphere to planetary chemists. When approaching the vast realm of Saturn, one of the key steps is to insert our spacecraft into orbit around the planet, then turn its attention to Titan. Orbital stabilization requires precise management of engines and trajectories. Once in orbit, the explorer begins a long series of maneuvers to approach Titan, a fascinating moon due to its imposing size and thick haze. At first glance, Titan reveals itself as a dark sphere, bathed in a dim light, filtering through multiple atmospheric layers. The contrast between the darkness of Saturn's rings in the background and Titan's pale glow evokes a science fiction scene. Yet, it is real. Titan orbits about 1,200,000 kilometers or 746,000 miles from Saturn on a stable elliptical trajectory. The first objective is to capture panoramic images to document its orange haze and identify major cloud formations. Wide-angle cameras provide global views, while spectroscopic instruments analyze the chemical composition of atmospheric particles, notably tholins. Before progressing, it should be noted that Titan is about 40% of Earth's diameter and exceeds Mercury, surprising those who typically associate a moon with a smaller body. Its size challenges our perceptions, revealing an almost planetary spherical object in the orbit of Saturn. To understand Titan's veiled appearance, we look at tholins, organic compounds formed by photochemical reactions in an upper atmosphere rich in nitrogen and methane. Solar radiation and the bombardment of energetic particles break molecules, releasing radicals that recombine to create brown or red organic particles. Over time, these particles condense, gather, and fall, forming Titan's characteristic haze. From Saturn's orbit, this veil acts like a curtain. You can guess the roundness of the moon, but the topography remains hidden. Engineers then resort to radar to map the surface beneath the haze. Radar waves penetrate the atmosphere with minimal absorption, revealing icy plains, dunes, and basins of liquid hydrocarbons. Preparing for descent involves accurately calculating trajectories, considering Saturn's gravity and the weaker gravity of Titan. Even though Titan is colder, its thick atmosphere generates significant friction during entry. Thermal shields and other protections are calibrated to withstand this trial. Upon penetrating the upper layers, composed mainly of nitrogen and light hydrocarbons, the probe experiences shakes due to turbulence, influenced by Titan's rotation and its high-altitude weather phenomena. Instruments measure temperature, pressure, and density, essential data for adjusting descent and enriching our scientific models. Titan remains one of the few bodies with an atmosphere dense enough to consider future aerial explorations, such as balloons or robotic helicopters, and samplers aim to collect tholin particles for analysis. As the speed decreases and cameras can operate more easily, the orange veil is fully perceived. Sunlight diffuses through the haze, creating a permanent twilight. Unlike Earth, there are no water droplets, but a mixture of aerosols, ultrafine dust, and exotic gases. Infrared cameras, on the other hand, provide glimpses of the ground. Dunes, polar regions, and basins of liquid methane appear through specific wavelength filters. Titan exploration is often compared to diving into an ocean of murky air. Like a diver seeking to discern what's hidden under an opaque sea, the probe must traverse layers where chemical properties and aerosol concentration vary until reaching the interface between the atmosphere and the surface. Even if the diver sea analogy is compelling, Titan is a frozen world, far from the sun, and composed of elements very different from those on Earth. In comparison, the formation of Titan and that of Mercury differ. Mercury, a rocky planet born near the sun, lost its initial atmosphere, while Titan, formed far in the solar system around a giant star, retained a thick atmosphere rich in nitrogen. The extreme cold limited gaseous losses and allowed the formation of tholin haze through photochemistry. The orange and brown hues are thus not mere artifacts, but the result of a permanent chemical dynamic. Viewed from orbit, Titan seems peaceful, slow movement, low brightness, and an apparently motionless silhouette. However, the descent reveals an active environment, chemical reactions, particle mixing, and sporadic rains of liquid methane or ethane. The challenge consists of coordinating braking, potential parachute deployment, and scientific measurements. Ground teams follow telemetry data in near real time to confirm the trajectory. Each adjustment depends on the increasing density of the atmosphere and local conditions, speed, pressure, temperature. Everything evolves rapidly in the lower layers of the haze. As the descent continues, one imagines Titan seen from space, a globe veiled by an orange light, now traversed by the probe. Sometimes, hydrocarbon droplets fall, hard to distinguish in the winds and clouds. The lower you go, the more the pressure increases and the visibility decreases, until perhaps spotting a clearing, like fog dissipating in a valley, or opacity reinforced by local storms. The probe, crossing these layers, approaches the ground, ready to unveil the geological and atmospheric backstage of a still mysterious world. It is surprising to recall that Titan, a satellite of a distant giant planet, exceeds Mercury in diameter. It is an autonomous world, endowed with seasons, active chemistry, and a persistent veil. The flyby is conducted with caution, as the intensity of winds and the thickness of aerosols remain uncertain. The opacity that makes Titan enigmatic from the darkness of orbit becomes a real challenge for instrumentation and navigation. The continuous deposit of tholins gradually shapes the relief and color of the landscape. This cycle of organic deposits could influence the availability of resources or the formation of complex molecules on the surface. Even before reaching the ground, the probe collects and analyzes these suspended particles to understand their role in organic pollution, that is, carbon enrichment. The low solar lighting, sufficient to sustain an intense flow of photochemical reactions, recalls early Earth and makes Titan a natural laboratory for studying prebiotic chemistry. In this long journey, the transition from high orbit to descent towards Titan is like moving away from a painting in a museum, then approaching to discern each brush stroke. Initially, Titan presents itself under a uniform glow. As we progress, we discover the richness of details, subtleties of colors, variations in fog thickness, different hues when the haze thins, revealing the diversity of the surface. Thus, the transition phase between orbital tranquility and immersion in this atmosphere, where extreme cold and permanent organic chemistry reign, concludes. The probe prepares to land or fly close to the ground to analyze the soil composition, a symbol of technological audacity and scientific curiosity. Observing Titan from space, comparing its size to that of Earth or Mercury, and highlighting its orange veil, already an achievement. And if this veil holds the keys to chemical evolution, the descent towards Titan becomes a decisive moment. Each piece of data, each molecule detected, and each image enriches our knowledge of this astonishing solar system. At first glance, Titan's exosphere and ionosphere may seem distant and inaccessible, but they form a gaseous shield protecting the moon from the space environment. At this plasma frontier, the sun's charged particles interact with the gases of the atmosphere. Let's follow step by step the importance of these regions and discover how recent observations have enriched our understanding of this ever-changing layer. Since the first missions, it has been known that nitrogen dominates Titan's outer layer. This molecular gas, composed of 2 nitrogen atoms, accounts for about 97% of the high-altitude air, which is more than on Earth's surface. Methane, acetylene, and hydrogen cyanide are also present. When exposed to sunlight or other cosmic particles, these gases become partially ionized, marking the beginning of the ionosphere, where electrical phenomena are crucial. Between 2023 and 2025, the ALMA Observatory in Chile measured the 2:14N 15N ratio in the nitrile molecules of Titan. This isotopic ratio, far from trivial, is fundamental for understanding how organic molecules, potentially prebiotic, form. This advancement, considered major, reveals a more evolved chemical environment than expected, rich in compounds related to the chemistry of life. At high altitude, the solar wind, a continuous flow of protons and electrons, encounters the magnetosphere of Saturn, from which Titan partially benefits. Its eccentric orbit sometimes exposes it more to radiation. These particles, by hitting nitrogen and methane, excite, ionize, or fragment them, creating new, more complex compounds. That is why Titan's upper atmosphere is often described as a laboratory of planetary organic chemistry. This partial bombardment by the solar wind generates a plasma tail. Ions and electrons stripped from gases are carried off into space, forming a trail directed away from the sun. Data from Cassini confirm this dynamic, showing that Titan constantly exchanges matter with space, not remaining just a fixed gaseous sphere. Cosmic rays originating from supernovae and black holes also penetrate this barrier. By entering the atmosphere, these energetic particles release their energy onto the gases, contributing to the formation of aerosols, fine organic particles in suspension, which then descend to feed Titan's characteristic orange haze. Titan's ionosphere reacts to solar intensity, which varies according to the seasons and the sun's activity cycle. When irradiance increases, the production of ions and electrons rises. When it decreases, ionization slows down. One can imagine an electrical tide modulated by Titan's position in Saturn's magnetic field and solar variations. Cassini showed that each morning, light partially restores this layer after the night. The recent measurements conducted by ALMA on the ratio between nitrogen-14 and nitrogen-15 isotopes provide a new perspective on the ionosphere. Beyond confirming the presence of nitriles, this isotopic ratio allows scientists to trace back to the origins of nitrogen on Titan. Researchers compare this process to a planetary paternity test. It aims to determine whether nitrogen comes from the outer reaches of the solar system or settled after the initial formation. These temporal and spatial clues enrich the chemical history of the moon. From a prebiotic standpoint, an environment laden with nitrogen, methane, and complex molecules is fascinating. Titan's upper atmosphere acts as an immense chemical chamber where solar radiation, solar wind, and cosmic rays simultaneously work. Each impact strips electrons, breaks or assembles molecules, generating a large inventory of carbon and nitrogen-based compounds which, over time, form long chains capable of descending to lower layers. In addition to solar and cosmic influences, Saturn's magnetic activity sometimes sends plasma flows to Titan. These charged bursts temporarily intensify ionization, causing a peak in aerosol production. Studying these magnetic storms helps understand how they redistribute chemical species and reshape the plasma boundary around Titan. Moreover, the ion density measured in the upper atmosphere sometimes differs from predictions. Occasionally, there are more or fewer charged particles than expected. This margin of error suggests the existence of unknown mechanisms such as rapid recombinations, dissipation to high latitudes, or novel interactions with Saturn's electric fields. Some even speculate that charged dust grains could create a solid particle ionosphere, adding further complexity. Despite this wealth of phenomena, Titan reaches a relative equilibrium. External energy from UV radiation, solar wind, and cosmic rays continuously produces and renews molecules, while some of them fall back or escape into space. One can imagine a gigantic atmospheric factory where production and evacuation succeed each other. The aerosols generated at high altitudes, charged or not, contribute to Titan's distinctive orange haze, visually illustrating the active chemistry at work. Between 2023 and 2025, ALMA has clarified the significance of the isotopic ratio in the formation of nitriles. These compounds, which combine a carbon group with a nitrogen atom, readily form in a nitrogen-rich environment. Present in small quantities, their spectral signatures reveal their key role in building larger organic chains. With each radio-infrared observation, new variations of nitriles are noted, evidence of multiple chemistries fueled by variable energy and particles. As research progresses, the understanding of this plasma frontier is refined. Future missions will study how the ionosphere evolves with Titan's seasonal changes, orbital position, and solar activity. Computer models, enriched by these recent data, show that the thermosphere can expand or contract, altering the height of the ionosphere. Solar winds, magnetic storms, and cosmic rays locally modulate the ion density and chemical reactions. Titan's elliptical oscillation around Saturn adds another dynamic. When Titan aligns with Saturn and the Sun, it remains better protected, which affects ion production. Finally, the impact of cosmic rays on aerosol formation is particularly interesting to exobiology. These particles can initiate complex reactions that give rise to sugars, amino acids, or other advanced molecules. While the upper atmosphere, at about 190 degree or 310 degree, is far from being conducive to life as we know it, Titan offers a unique natural laboratory for studying organic chemistry outside an oxygen-rich context. Titan's stratosphere, located between about 50 kilometers, 31 miles, and several hundred kilometers, hundreds of miles, in altitude, is a fascinating universe where chemistry and physics blend to produce unique phenomena. At around 250 kilometers, or 155 miles, the temperature reverses its trend. Instead of dropping with altitude, it temporarily rises to about 203 degrees Celsius or 333 degrees Celsius before falling again. A similar phenomenon exists in Earth's stratosphere, but its causes differ. On Titan, This inversion results from the absorption and re-emission of solar radiation by certain gases at specific altitudes. Although Titan receives less light than Earth, its dense atmosphere retains and redistributes heat in a complex way. At these levels, the sun, though weak, triggers photochemical reactions when its ultraviolet rays strike molecules. Methane, central to atmospheric dynamics, is the primary initiator of these transformations. When sunlight interacts with methane, it breaks this molecule into highly reactive free radicals, true natural building blocks that recombine with each other or with other molecules in the stratosphere. Over these reactions, methane transforms into ethane, benzene, and a series of other complex carbon-based hydrocarbons, collectively referred to as organic aerosols. These microscopic particles float in the air, forming the hazy shroud that gives Titan its orange coloration, as seen in probe images. The term photolytic cascade is used to describe this sequence. Photolysis, or decomposition under light, strikes a methane molecule, releasing one or more atoms depending on the energy received. These fragments become active entities, ready to combine. Intermediaries, such as various light hydrocarbons, appear before giving rise to heavier compounds like ethane, benzene, or solid particles akin to volcanic soot, though their origins differ. All these products contribute to a stratospheric haze, whose thickness and density vary according to the seasons and solar intensity. Beyond their aesthetic interest, these hazes reveal the chemistry of Titan. Scientists are striving to map the distribution and abundance of these molecules since they provide information on the long-term evolution of the atmosphere. Recently, attention has been focused on benzene, this aromatic hydrocarbon, a ring of 6 carbons with 6 hydrogens, familiar on Earth but toxic at high doses, forms at high altitudes before joining the haze. To study this chemistry more closely, cutting-edge instruments covering different wavelengths are being relied upon today. This is the role of the James Webb Space Telescope, JWST, operational since the mid-2020s. Its infrared detectors will allow, by around 2025, global mapping of Titan's polar hazes, aiming to detail the distribution of benzene and other organic derivatives in the upper atmosphere. These polar hazes are of particular interest because Titan's tilt and seasons shift chemical activity from one pole to the other. Since Cassini, it has been known that polar regions are rich in clouds and hydrocarbon-related phenomena. By refining stratospheric infrared imaging, researchers hope to understand how the sun triggers and sustains these reactions, and how seasonal variations influence their formation. The data will be compared to atmospheric models to adjust our scenarios concerning the past, present, and future of this icy moon. The announcement of JWST observations for Titan has generated great enthusiasm. Its infrared capabilities far surpass those of traditional ground-based telescopes. They are ideal for probing the cloud structures and identifying the spectral signatures of molecules. When light passes through the haze, each chemical species absorbs specific wavelengths, creating a fingerprint in the spectrum. These data will reveal the abundance of aerosols, ethane, and benzene in the stratosphere, and give clues about other, more complex molecules. The first expected results from these global maps should confirm the calculations of previous missions, while providing new details on the distribution of clouds and chemical reactivity above 100 to 200 kilometers, 62 to 124 miles in altitude. The objective is to link observation and the laws of physical chemistry. If the concentration of methane differs from predictions, the goal will be to identify the responsible mechanisms, seasonal variations, electrical contributions from lightning, or atmospheric basins trapping certain gases. This veiled atmosphere has earned Titan the expression extraterrestrial smog, reminiscent of the polluted fog of Los Angeles in the 1960s. Although there is no human activity, this dense particle-laden haze results from natural processes. It contains ethane, benzene, and numerous complex hydrocarbons formed in the stratosphere before descending. In the absence of free oxygen, these carbon-based molecules persist and accumulate, forming organic flakes that eventually fall on the dunes and poles. Though the smog of Titan is not industrial, this comparison helps raise public awareness that toxic hazes can naturally arise under different planetary conditions. It has also inspired science fiction stories depicting Titan as a dark world. In reality, the surface still receives some light thanks to diffusion in the haze, and studying the stratosphere is essential for understanding how this opaque veil is created and renewed, which sometimes disrupts instrumentation. Between the temperature inversion at a few hundred kilometers, miles, and the photolytic reactions of methane forming ethane, benzene, and aerosols, Titan's stratosphere perfectly illustrates the dynamics of an active atmosphere. This region acts as an interface between the exchanges of the troposphere clouds of methane and interactions with solar or cosmic particles. Every discovery about the stratosphere sheds light on Titan's chemical history. Measuring the relative abundance of certain organic compounds provides clues on how, over billions of years, this moon has accumulated elements essential to prebiotic chemistry. Past investigations, notably thanks to Cassini, have provided the first pieces of the puzzle, but recent and future tools, like the JWST, offer a fresh perspective, with superior resolution and sensitivity. Researchers are relying on infrared imaging to identify the stratospheric zones most active in aerosol formation and to quantify the speed of the photolytic cascade. They also hope to detect other unknown compounds. Ultimately, cross-analysis of the data will refine numerical models simulating all atmospheric processes, from light absorption to the formation of opaque haze. In the end, this photochemical stratosphere is more than just a simple layer. It is a natural laboratory where carbon chemistry and unique atmospheric phenomena intertwine. At the inversion altitude, where the temperature reaches about 230 degrees or 334 degrees, and methane transforms relentlessly, generating the range of compounds needed for Titan's haze. The ever-changing polar hazes largely depend on these reactions to sustain themselves and slowly migrate from one region to another. In this distant setting, referred to as extraterrestrial smog, a continuous chemical choreography unfolds. Observations from the JWST, combined with those from other space missions or ground-based telescopes, promise to shed more light on these extraordinary phenomena. Understanding the role of methane, ethane, and benzene in haze formation is essential to grasp the long-term evolution of Titan's atmosphere. Each new stratospheric discovery enriches our overall vision of this moon, whose shrouded ambience continues to stimulate human curiosity. In the future, spacecraft flying by Titan again will carry this data to better forecast its exceptional weather and deepen our knowledge of carbon chemistry beyond Earth. Titan's troposphere is the lowest and most active layer of the atmosphere of Saturn's satellite. It exerts a ground pressure of about 1.45 bar or 21 psi, slightly higher than that of Earth, revealing a gaseous veil dense enough to generate complex meteorological phenomena. We will explore step by step the behavior of this troposphere, what makes it unique in the solar system, and how its study offers fascinating perspectives for understanding atmospheric dynamics beyond Earth. At the heart of this troposphere, the average temperature hovers around 179 degrees or 290 degrees. Such cold would be fatal to terrestrial life forms, but it does not prevent an active meteorological cycle relying on hydrocarbons like methane and ethane. On Titan, these substances play a role similar to water on Earth. They evaporate, form clouds, and then fall as rain, shaping the landscape and contributing to the respiration of this world. Grasping this cycle requires understanding both the analogies and the differences between the chemistry of water and that of methane. On Earth, water evaporates under the effect of the sun, rises, condenses into clouds, and then falls as rain. On Titan, the fainter sunlight causes the evaporation of liquid methane mixed with ethane and other hydrocarbons, and it's this polar troposphere that determines cloud formation. Although this dynamic is far from earthly norms, it creates often turbulent weather. Probes and telescopes have revealed transient clouds, sometimes stretching over several hundred kilometers or miles. The slow winds, modulated by Titan's rotation and Saturn's gravity, move these clouds far from their origin. The denser atmosphere keeps microdroplets of hydrocarbons suspended, giving the sky a misty and milky appearance, accentuated by the low solar brightness. When clouds accumulate enough particles and gas, precipitation occurs. It is not water, but rain of methane mixed with ethane, or even more complex compounds. The rare direct observations come from the Huygens probe in 2005 and flybys of the Cassini mission over more than a decade. They have highlighted a meteorological phenomenon whose intensity varies according to a seasonal cycle of 29 Earth years, the duration of a Saturnian year. In this long seasonal waltz, the boreal summer on Titan brings prolonged sunlight to the north. The surfaces of liquid methane, seas, lakes, wetlands, evaporate more actively then. The air masses, filled with hydrocarbon vapor, rise into the troposphere and form vast clouds. In May 2025, a radio-optical network detected intense cloud convection over the northern lakes. The increasingly sensitive instruments measured the density and size of these formations, showing that the clouds were forming much faster than expected. This discovery highlighted Titan's ability to generate significant thunderstorms. On Earth, thunderstorms form when moist air rises, cools, and triggers rain and lightning. On Titan, the principle is similar, although the raw material is methane and the extreme temperatures slow some processes. Yet these same convective forces create imposing clouds, which fall back as showers over vast areas, carving the ground, sculpting valleys, and feeding lakes and seas of hydrocarbons. In the boreal summer, the relative warmth in the northern hemisphere intensifies evaporation. Methane can rise to high altitudes, encounter cooler zones, and condense into impressive storms. The atmospheric density and the slow seasonal cycle allow these storms to form gradually and persist longer than on Earth. Additionally, Titan exhibits an asymmetric distribution of lakes between the poles. The North Pole is particularly rich in hydrocarbon bodies, probably linked to past climatic variations. When this pole receives more solar energy, evaporation speeds up, producing large clouds capable of spilling over beyond the polar region. Modeling suggests the existence of mega-rains. They occur when maximum methane vaporization, the arrival of a colder air mass, and a strong pressure gradient align. The hydrocarbon droplets then quickly accumulate and fall as torrential rains over extensive areas. These mega-rains could erode hills, create or expand seasonal rivers, and reshape certain basins in a few weeks or months, contributing over several years to marked surface erosion, comparable to that induced by several successive tropical storms on Earth. To understand why such storms erupt, one must consider the thermal behavior of the troposphere. With weak solar radiation, a slight surface warming, combined with residual internal heat, is enough to initiate the ascent of methane and ethane-laden air. Seasonal data indicate that the temperature differences between day and night, associated with Titan's rotation, stimulate the formation of powerful winds. As they rise into the troposphere, these hydrocarbon masses encounter cold zones, quickly condense, and form clouds. Astronomers and planetary scientists then combine radio telescope observations, embedded infrared cameras, and climate simulations to reconstruct this atmospheric choreography. Boreal summer thunderstorms are sometimes accompanied by lightning, although their existence is still debated. Theoretically, electrical discharges can arise from the friction of particles in methane clouds. Some signals detected by Cassini and relayed to terrestrial networks suggest the presence of electrostatic phenomena, much less frequent and powerful than on Earth. If a few lightning bolts traverse Titan's atmosphere, they would contribute to the formation of new chemical compounds by fragmenting hydrocarbons similar to terrestrial lightning breaking nitrogen and oxygen. Measurements remain difficult to interpret, but upcoming data should shed light on this subject. It is fascinating to observe that these meteorological phenomena interact with the very structure of the troposphere. With high pressure for an object of this size and very low temperature, the condensation point of methane is close to the actual conditions. A slight warming or a small atmospheric composition variation can trigger rapid cloud formation. This sensitivity reinforces the idea that Titan experiences sudden, rainy episodes. An apparently calm atmosphere can suddenly give way to violent storms. Over the years, instruments have advanced. Observations of cloud convection from May 2025 illustrate our ability to monitor Titan's sky in near real time. Ground-based telescopes, now aided by space observatories, can see in wavelengths invisible to the naked eye. When radio signals indicate increased opacity in certain regions, astronomers trigger infrared imagery to confirm the presence of clouds. Radiative transfer models then evaluate the amount of precipitated hydrocarbons. Thus, we map the troposphere with increasing precision and predict the intensity of future storms with growing reliability. A crucial aspect of studying this troposphere is the analogy with primitive Earth. Several billion years ago, our planet had a very different atmosphere, populated with clouds laden with organic compounds. On Titan, we observe a modern and scaled-down version of this ancestral climate, dominated by methane. The mega-rains of 2024 remind us with nuances of the storms that shaped early Earth's geology. Understanding how a closed hydrocarbon cycle operates sheds light on Earth's past and life's resilience. The observation of Titan remains a logistical challenge. The distance to Saturn reduces the resolution and frequency of direct measurements. Nevertheless, Cassini, which appeared between 2004 and 2017, provided a wealth of data, including on cloud convection. Since then, astronomers have been waiting for the next step to scrutinize the troposphere and discover new formations. The summer northern hemisphere storms could reveal new peculiarities in upcoming seasons. Cyclic methane precipitation is already the subject of multiple hypotheses, and future articles will clarify the extent of these phenomena. For now, climate simulations suggest that with the return of sunlight to the northern hemisphere, large storm cells will reappear in the troposphere. This extended seasonality, combined with complex exchanges between the surface and atmosphere, may hold surprises yet. Some even predict rare episodes where Titan's own rotation would intensify the collision of hydrocarbon-saturated air masses, leading to torrential rains. There is much to learn, especially since Huygens only offered a limited sampling of the surface and troposphere. Ultimately, the results of these atmospheric manifestations will enrich not only our understanding of Saturn, but also the reflection on the evolution of planetary atmospheres. Titan is one of the few bodies with active meteorology. Its study will further unveil mysteries about the processes that may have occurred during the genesis of Earth. Researchers from Nature Geoscience and other specialized journals plan to explore the mega-rains and their geological impact. These exceptional accumulations could transform entire regions, shaping hills and methane rivers. Above Titan's icy surface, a thick veil of organic aerosols called tholins extends over several hundred kilometers or miles. These particles, formed from a mixture of carbon and nitrogen molecules transformed by sunlight, cosmic rays, and other chemical processes, give Titan its characteristic orange tint and obscure the view toward the ground. To understand these hazes, one must explore their structure at altitude, their optical properties, their fabrication in the laboratory, and their effects on the surface. In orbit around Titan, it is observed that the haze is distributed in two layers. The detached haze around 500 kilometers or 311 miles altitude, almost independent of the rest of the atmosphere, and the main haze peaking around 300 kilometers or 186 miles. The detached haze appears as a diaphanous veil, formed in conditions where residual solar radiation favors chemistry. Lower down, the main haze is denser, rich in particles, and nearly completely obscures the surface. It creates the deep orange seen from space. These hazes derive their color from tholins. Named as such, since laboratory experiments replicating primitive planetary atmospheres, these compounds are born when methane and nitrogen react under the influence of ultraviolet light and cosmic particles. Carbon chains form, lengthen, and aggregate into solid orange grains. Suspended, these tholins absorb or scatter certain wavelengths, reinforcing the orange veil effect. From the surface, the sky appears veiled, colored, distinctly different from ours. These particles also play a role as a filter against ultraviolet rays. By reducing the penetration of the most harmful rays, they affect the chemistry of the lower layers and moderate the temperature. Thus, the haze traps some of the heat, maintaining Titan in a cold and stable state around 180 degrees Celsius or 292 degrees Fahrenheit while regulating the exchanges of energy and matter with space and sunlight. In the laboratory, scientists reproduce these tholins to identify the molecules that form these particles. Inspired by the 1952 Miller-Urey experiment, which showed that a mixture of gases subjected to electrical discharges can generate organic molecules, they now use mixtures similar to Titan's atmosphere, nitrogen, methane, and sometimes other carbon gases, exposed to temperatures close to 180 degrees Celsius or 292 degrees Celsius, and to energy sources simulating ultraviolet rays or solar wind. They then observe the formation of solid particles resembling titanium tholins. In these small-scale experiments, simple molecules react, create more complex molecules, and then aggregate into carbon droplets or particles. Gradually, these grains evolve into solid structures. At the end of the reactions, an orange-brown deposit remains. Although these conditions do not perfectly replicate those of Titan's atmosphere, solar wind, gravity, and complex circulation are missing. These experiments shed light on Titanian chemistry and help formulate hypotheses on the evolution of tholins. These grains do more than just play an atmospheric role. They fall back as snow onto the surface, similar to organic powder rather than water ice. The equatorial dunes, for example, are made up of dark grains where ultra-hard water ice and organic sediments are mixed. Radar and infrared images from Cassini show these regular coatings of the landscapes. In the extreme cold, these particles retain their chemical structure and accumulate in layers over time. This organic snow could play a role in Titan's chemical fertility. On Earth, rain delivers nutrients. On Titan, this organic deposit, associated with the hydrocarbon liquids of polar lakes, could initiate prebiotic chemistry. Even though the absence of oxygen and the low temperatures seem unfavorable to terrestrial life, these sediments could serve as starting points for more complex reactions, paving the way for still unexplored prebiotic mechanisms. Let's return to the structure of the hazes. Around 500 kilometers or 311 miles of altitude, where the pressure is low and the solar irradiation more intense, the formation of tholins follows a direct pattern. UV and charged particles break the bonds in methane and nitrogen, creating free radicals that generate the first stages of chemistry. The very low temperatures favor the condensation of certain carbon and nitrogen chains. The suspended haze remains in suspension thanks to high-altitude atmospheric currents, which slowly redistribute the aerosols in the gaseous envelope. Descending to 300 kilometers or 186 miles, the main haze becomes denser. It accumulates aerosols from the upper zone, and those produced locally by other photochemical reactions or under the impact of lower cosmic rays. The escape rate to space is low. Titan's gravity, weaker than Earth's but sufficient, retains most of the particles. The layer then becomes more opaque, reinforcing the orange veil. Before Cassini-Huygens, many imagined the surface to be uniform, perhaps liquid. It was the study of the hazes that revealed a more complex world than expected. The ultraviolet filter exerted by these tholins in the main haze moderates the destruction of methane in the medium term. These high hazes absorb much of the UV before they reach the troposphere. The exact mechanisms of methane renewal on Titan are still debated, but it is clear that aerosols play a role in regulating atmospheric chemistry. When they fall, particularly in polar or equatorial regions, these tholins can be trapped by methane or ethane rains and mix with these precipitations, seeding the surface. Over millions of years, some of these organic sediments join the lakes, while others remain mixed with the pure water ice that makes up the crust. The polar regions sometimes show clearer surfaces, covered with organic residues mixed with ice. Depending on the proportion of aerosols, these deposits can appear barely visible or give darker and orangish hues. Despite a temperature around 180 degrees or 292 degrees Fahrenheit, Cassini-Huygens provided valuable information. During its descent in 2005, Huygens measured the density of the atmosphere and the scattering of light by the haze. Cross-referenced with Cassini's spectrometer in orbit, these data confirmed that the particles in the upper haze differ from those in the lower haze in their size, shape, and chemical complexity. The high-altitude grains are smaller and rich in nitrogen compounds, whereas those around 300 kilometers or 186 miles are larger and denser. final descent of these tholins creates a landscape covered in a fine organic powder. Over time, this deposit accumulates. In the equatorial dunes, it mixes with water ice and other organic materials. In the plains, it forms vast expanses reminiscent of constant dusting. The spectral variations detected by Cassinian radar and infrared mode show several types of terrain and degrees of tholin coverage. This dynamic is slow. It takes thousands or millions of years to shape the global appearance of Titan. But it can be summarized. The upper atmosphere produces organic particles, the upper haze accumulates them, the main haze concentrates them, and gravity brings them back to the ground as organic snow. This cycle contributes to Titan's chemical equilibrium and sculpts its orangish, hazy landscape. In a perspective of future exploration, understanding tholins will be crucial. The engineers and scientists preparing the drone helicopter planned to fly over Titan will need to know the exact composition of these hazes. Interpreting in situ data will require knowledge of the formation, aggregation, and fall of aerosols. Future samplings could reveal the chemical reactivity of this material and its prebiotic potential. Even without oxygen and at very low temperatures, these tholins could indicate intriguing chemical pathways. When the Cassini probe reached Titan, the nature of its surface initially remained a mystery. From Saturn's orbit, the thick haze surrounding this moon revealed only a dimly lit disk, without disclosing what was underneath. However, astronomers suspected the existence of varied terrains. Confirmation came only with Cassini's radar, used from 2004 to 2017, which managed to pierce the orangish veil and produce an unprecedented map. The albedo variations revealed dark regions and much brighter ones, providing researchers with an astonishing panorama. Ground-based observations hinted at icy zones and others rich in organic compounds, but without precise instruments, these hypotheses remained speculative. The arrival of Cassini and its synthetic aperture radar finally equipped scientists to measure the extent, shape, and distribution of these mysterious terrains, marking the transition from exploration based on assumptions to concrete knowledge. One of Titan's striking features is the contrast between its dark and bright terrains. Radar data show that the dark regions are mainly concentrated around the equator. These are dune fields shaped by winds, composed of organic grains akin to fine carbon particles. Their low light reflection gives them a very low albedo. In contrast, the brighter terrains, spread across various latitudes, reflect significantly more light. Scientists estimate that they are mainly composed of water ice, made extremely hard by the very low temperatures. This color and brightness opposition illustrates the chemical and geological diversity of Titan, a rare complexity among the moons and planets of the solar system. The boundary between dark and bright zones can stretch over hundreds of kilometers or miles, indicating processes of organic matter deposition and transport varying with latitude and local environment. Some bright sectors even show darker veins, signs of interactions between deep ice and more recently deposited materials. Each radar sweep thus adds a piece to the puzzle of Titanian topography. Between 2004 and 2017, Cassini flew over Titan numerous times, producing radar mapping that covers about 67% of the surface. A significant portion remains unknown. The radar emits waves at certain frequencies, penetrating the haze and returning echoes that describe the terrain's morphology. With each pass, the probe swept vast portions of terrain, revealing plains, valleys, and dunes stretching over several hundred kilometers or several hundred miles. The uncovered areas remain to be discovered, still sparking the curiosity of researchers who hope one day to unveil the full geological diversity of Titan. Cassini's trajectories were adjusted to obtain the best possible resolution, and the radar strips recorded over the years were assembled into a mosaic representing the most detailed view of Titan's relief to date. Despite the magnitude of the task, the time spent studying Titan was limited because Cassini pursued other objectives in Saturn's system. NASA, ESA teams, and their international partners worked tirelessly to interpret these images and refine their geomorphological models. Even today, these data are a valuable resource for understanding the formation and evolution of these unique landscapes in the solar system. The bright plains detected by radar, later confirmed by other methods, have a significantly higher albedo than the equatorial dunes. Scientists believe their brightness comes from an abundance of solidified water ice, forming a compact crust, sometimes covered by thin layers of organic compounds. In these regions, the temperature is around 180 degrees or 292 degrees, making the ice extremely hard and slowing most chemical erosion processes. At these latitudes, the ground appears more uniform, with fewer topographical variations than in the dune zones. However, the radar sometimes reveals discrete craters or modest reliefs, proving that these surfaces are not entirely flat. The interactions between ice and organic deposits produce complex structures, where the chemical composition evolves slowly under the influence of weak heat and cosmic radiation. While these changes are very slow on a human scale, they testify to Titan's geological history, marked by phases of ice accumulation and physical alterations. The bright plains, rarer than the dark zones but visually striking, are a major clue to this moon's environmental richness and diversity. Another essential aspect of Titan's landscape lies in its dark dune fields. These stretches can extend over several hundred kilometers or several hundred miles, mainly near the equator. Their pronounced hue is due to the low amount of light they reflect, contrasting sharply with the brighter, icy plains. The dunes result from the accumulation of organic particles from the upper atmosphere, gradually precipitated to the ground. Over time, winds, influenced by Titan's rotation and its moderate gravity, have arranged these particles into long bands. The topography of the dunes is not uniform. Linear dunes can be distinguished, and sometimes more complex structures, reminiscent of certain terrestrial desert forms. The presence of organisms in these sands raises questions about Titan's internal chemistry and the atmosphere's role in the fragmentation and aggregation of these molecules. In the radar images, corridors carved by the winds, elevated ridges, and transition zones where dunes give way to different terrains can be perceived. Overall, these dark fields evoke a vast extraterrestrial desert where orange dominates, reinforcing the impression of a world entirely foreign to terrestrial landmarks. For any probe or vehicle intending to land on the surface of Titan, risk assessment is crucial. Radar surveys from Cassini have highlighted potentially perilous surfaces, notably soft areas where a lander might sink. In sandy regions, the cohesion between organic grains is sometimes insufficient to provide solid support. Near hydrocarbon lakes, steep slopes detected suggest that the banks may be unstable, especially in the presence of methane and ethane-rich liquids. Add to this temperatures often below 170 degrees or 274 degrees, and the challenge of a smooth landing becomes enormous. Designers of future missions are considering solutions adapted to this extreme environment. The craft will need to withstand the intense cold and unpredictable mechanical conditions, such as loose terrains or irregularities masked on a radar scale. The atmospheric pressure, slightly higher than Earth's, does help to slow the descent, but does not guarantee a stable contact zone. The risks are not limited to the ground's solidity. The ambient chemistry, hydrocarbon humidity, and the danger of slipping on ice also come into play. Each attempt to land on Titan is thus a technological and environmental challenge, requiring an in-depth study of each potential site. Titan's cryogenic temperature, often around 180 degrees or 292 degrees, strongly influences the surface properties. At this extreme cold, water ice behaves like rock, and organic deposits become solidified. Instruments from Cassini show that these low temperatures slow surface chemical reactions, limiting the rapid creation of new geological structures. Moreover, the thermal contrast between day and night remains weak due to attenuated solar radiation and thick fog. Consequently, erosion related to temperature variations is very slow, preserving the relief shapes over long periods. However, in areas where hydrocarbon liquids flow, dissolution and mechanical erosion can locally transform the landscape. Scientists believe that despite this general slowness, Titan's terrain still evolves over very long timescales. The intense cold, therefore, remains a key parameter for the success of a landing and the survival of any probe on this exotic soil. In the end, Titan's panorama reveals itself to be rich and varied. Whether it's dark dunes or frozen plains, each area invites thorough exploration, offering unique features to discover. In the heart of the high latitudes, Titan's landscape changes radically, revealing liquid expanses similar to small seas. Here, everything seems frozen under temperatures around 107.9 degrees or 290 degrees, a climate where an ocean of water would be impossible. Yet, Titan shows astonishing vitality, notably in its northern polar regions, where vast seas and numerous lakes concentrate. Named Kraken, Ligeia, and Punga, these polar seas sometimes reach more than 300 millimeters or 984 feet deep. Behind these names evoking a distant universe, one finds not water, but a mixture of methane, ethane, and liquid nitrogen. These three components form a unique hydrocarbon hydrological cycle, giving Titan the only known stable lakes outside Earth. To understand the existence of these seas, we must recall their discovery. The first flybys of Titan by Cassini lasted over a decade, but it wasn't until radar images capable of piercing through the haze that large, smooth surfaces, characteristic of liquid bodies, were spotted. Kraken Mare thus appeared as Titan's largest ocean, followed by Ligeia Mare and Punga Mare, all located at the North Pole. This choice is not by chance. At the pole, the thermal and geographic configuration favors the conservation of volatile liquids, much like Earth's polar caps preserve ice. On Titan, the very low temperature solidifies most substances, but methane remains liquid, offering a polar landscape both mysterious and fascinating. In 2024, a radar study from Cornell University, reported by Nature, showed the existence of seasonal waves on the surface of Kraken Mare. Until then, it was thought that the weak winds and the viscosity of the mixture prevented any noticeable agitation. However, these waves, although moderate compared to Earth's oceans, prove that Titan is not static. Winds can rise and create a slight ripple, while temperature variations change the density of the liquid. When the temperature changes, the solubility of nitrogen in the methane and ethane mixture varies, disrupting the surface balance and amplifying the wind's effect on these vast expanses. This discovery highlighted the importance of monitoring seasonal effects on Titan. Following its orbit, the Moon undergoes climatic oscillations similar to Earth's seasons but longer. The frozen surface occasionally warms by a few degrees, or about 5 to 10 degrees, altering the gas dissolution in the seas. These subtle exchanges cause the lake's levels and hydrocarbon salinity to vary. Some researchers even suggest that nitrogen bubbles, formed when the gas comes out of solution, could cause slight fizzing on the surface of Kraken Mare and Ligeia Mare. These clues, even minor, signal a more significant internal dynamism than previously imagined. The Huygens probe provided complementary evidence in 2005. During its historic descent, it landed not far from these large seas, in a region where the data suggests it might have been crossed by rivers or watered by hydrocarbon showers. Huygens took images showing rounded pebbles, made mostly of solid ice, polished by past liquid currents. On Earth, such pebbles form in riverbeds where water rounds them over time. On Titan, it is likely liquid methane and ethane that played this mechanical role, revealing the existence of an active cycle of precipitation, flow, and sedimentation. The chemistry of these polar lakes also fascinates specialists. On Earth, water is the main solvent of life and shapes geology. On Titan, water is a crust material, extremely hard, while liquid methane and ethane fulfill the role of water. Nitrogen, the major gas in the atmosphere, partially dissolves in these seas, depending on temperature and pressure. Researchers are closely studying these solubility coefficients to understand how bubbles appear and how liquid density varies. Every nitrogen fluctuation has a significant impact on the dynamics of these polar regions. Another fascinating aspect concerns the presence of benzene and tholins in these seas. Benzene under terrestrial conditions is a delicate aromatic hydrocarbon, but on Titan, it can precipitate and dissolve in the methane and ethane mixture. When the temperature drops below 90 K or 298 degrees Celsius, benzene becomes more soluble and crystals can appear if it drops further. As for tholins, these are organic particles formed in the upper atmosphere under ultraviolet and energetic particle action. Falling like a dusty haze, they color Titan with a characteristic orange. In the seas, tholins can settle or dissolve, contributing to the chemical composition of the bottom and shores. Their presence suggests that these lakes are the stage of complex chemical interactions, still poorly understood. In the laboratory, it has been shown that precursor molecules of prebiotic chemistry can assemble in these cryogenic solvents, opening the way to unexpected discoveries. This chemical complexity is also reflected in the physical properties of the polar seas. Radar measurements often record subtle variations in reflectivity, indicating the viscosity of the mixture and the presence of dissolved materials. Albedo differences suggest that the seabed is not uniform. There may be sediments rich in organic matter, somewhat like the mud of Earth's sea floors. On Titan, low gravity allows these deposits to spread widely, while methane cycles offer opportunities for transport and deposition unmatched on Earth. The shores of Kraken Mare raise many questions. Radar images and altimetric data sometimes draw sharp contours, suggesting cliffs or steep banks. On Earth, coastal erosion forms beaches, rocky coasts, or sandy deltas. On Titan, the retreat or advance of the seas, influenced by the seasonal climate, can create marked traces, sediment deposits, ice block polishing, or temporary marshy areas. Since the liquid has a different density, the waves would behave differently from those of our oceans, generating unique coastal shapes. Another mystery comes from the depth of these seas. For Kraken Mare, depths of nearly 300 meters or 984 feet are estimated, but this estimation is based on the interpretation of the radar signal passing through the liquid. Scientists are working to refine these measurements through reflection and wave propagation techniques, while taking into account the exact chemical composition. The more dissolved elements the liquid contains, the more it absorbs the energy of the signal, skewing the data. This is why future missions, like the conceptual submarine Talus, are being considered to explore these depths, offering a precise view of the liquid stratification and any solid deposits. The idea of layers of tholins accumulated over millions of years or traces of ancient climate variations already captivates planetologists. Understanding the chemistry of these lakes is also crucial to assessing the possibility of even rudimentary life. Without oxygen or liquid water, terrestrial life seems impossible, but some protocols suggest that exotic reactions fueled by liquid methane and ethane, catalyzed by tholins, could occur. Testing this hypothesis will require instruments capable of sampling the liquid at different depths and analyzing the subsoil. Current data motivate new missions, sometimes still in the project stage, which could reveal unexpected mechanisms of organic molecule formation in these cryogenic environments. Today, by scrutinizing the radar echoes more closely and comparing our maps of the polar lakes to those of terrestrial coastlines, Titan nourishes the hope of major discoveries. Each new observation, whether it be detected waves or singular deposits, refines our understanding of the unstable equilibrium reigning in these hydrocarbon seas. Over the years, the image of an inert satellite has given way to that of a vast alien sea, familiar by its liquid aspect and surprising by its composition. Step by step, our knowledge of Kraken Mare, Ligeia Mare, and Punga Mare extends our fascination with extraterrestrial chemistry. The adventure is just beginning. Future missions, better equipped to probe these expanses, could transform our vision of what an ocean can be beyond Earth. And if, one day, diving into a polar lake on Titan became a reality, we could then admire these icy pebbles, these fleeting waves, and that orange haze from the very surface of this distant world where meteorology and geology challenge all our references. This is the promise of Titan's polar seas and lakes, an exploration space at the frontier of science and imagination, witnessing a fascinating chapter in the unfinished story of this captivating moon. In the heart of the vast, icy expanses of Titan, one of Saturn's moons, an unexpected spectacle unfolds. A network of rivers and winding valleys carving the surface, forming deltas that testify to an intense fluvial past. Despite temperatures around 179 degrees or 290 degrees and a nitrogen-rich atmosphere, Titan displays surprisingly familiar reliefs. Around Ligeia, one of the most extensive hydrocarbon seas, probes have uncovered a network of channels, valleys, and numerous sedimentary deposits, precious clues for understanding the flow cycle and the unique fluvial climate of this distant world. To immerse the viewer in this geological history, one must first describe how these landscapes have been shaped by unusual liquids, then explain the mechanisms that created and reshaped these formations over time. On Titan, the fluid that carves into the ice is not water, but a mixture of hydrocarbons, primarily methane and ethane, which remain liquid on the surface due to extreme temperatures. Water, almost always frozen, makes up most of Titan's crust. When methane and ethane condense in the atmosphere and fall as rain, they sculpt the surface by carving out riverbeds reminiscent of our rivers. This hydrocarbon cycle operates like the water cycle on Earth, but with different compounds. Around Ligeia, this cycle is clearly visible. The region receives enough precipitation to regularly feed channels that flow into the hydrocarbon sea. By examining radar images and mappings from probes, Scientists have identified a dendritic network around Ligaea, a set of channels branching out like tree limbs. On Earth, these patterns appear where erosion acts on a homogeneous substrate. On Titan, they show that the surface layer, composed of water ice at these temperatures and covered with organic sediments, is gouged by the liquid hydrocarbons. As they flow along slopes, the methane and ethane pull away material grains, slowly carving the terrain and eventually forming extensive valleys. This mechanical alteration, due to flow and transported particles, requires thousands or even millions of years to give rise to such vast and branched valleys. As these successive flows progress, the detached materials are carried to lower areas where the current slows and deposits the sediments. This is where deltas form, cone-shaped or fan-like structures at the watercourse mouths, similar to those seen on Earth. In this location, several formations suggest deltaic deposits, areas where sediments have accumulated in layered deposits. These strata reflect the history of cycles of filling and drying. Like on Earth, during heavy floods, a river concentrates a large amount of sediments that it deposits in a fan before retreating, leaving a delta. On Titan, these cycles may last much longer, but the principle remains the same. The deltas testify to intermittent methane and ethane rains that have shaped the landscape and retreated several times before returning to reshape the topography. To measure the extent of these fluvial phenomena, it is useful to compare with well-known terrestrial examples. The Nile, for example, is an iconic river of active delta formation. When flying over the Nile Delta region, one sees how the river branches into a fan, feeding the Mediterranean. On Titan, the configuration is not the same, but the ice layer covered with organic sediments is gouged by hydrocarbon flows, creating valleys similar to those of the Nile. Seasonal methane and ethane rains swell these rivers, which carry sediments over several kilometers or miles before emptying into Ligaea, forming a delta comparable to that of the Nile, although the transported material differs radically. The Mississippi offers another illustrative example. This winding river, crossing the North American plains, widens as it approaches its mouth, forming lobe-shaped deltas jutting into the Gulf of Mexico. On Earth, the alternation between high and low waters, coupled with sediment input, constantly shapes the coastline. On Titan, imagining a hydrocarbon version of the Mississippi, one envisions methane rains, supporting a powerful flow, capable of transporting sediments over great distances before they settle upon contact with Ligaea. With each new cycle, the delta adjusts, shifts, or reforms, leaving layers of deposits detectable by radar. These comparisons do not assert that Titan is a mini-Earth. They show that the laws of fluvial geomorphology apply even in a world where water is replaced by hydrocarbons and where ice acts as rock. This is the essence of the scientific approach: to observe familiar forms, deduce the processes, and then compare to understand how nature shapes landscapes under very different skies. The cycles of filling and drying on Titan result from local climatic fluctuations, governed by Titan's orbit around Saturn and by the tilt of its axis. The seasons there are longer than on Earth because Saturn takes many years to complete its revolution around the Sun. Thus, periods more favorable to methane rains are followed by relatively drier phases, altering the level of channels in Ligaea. Around Ligaea, the deltaic deposits are often in the form of terraces or small staggered reliefs, reflecting the superposition of ancient fluvial levels. Researchers observe these variations thanks to probes that use radars able to pierce the haze of Titan, as well as by studying the reflectivity and chemical composition of these surfaces. In some areas, abandoned channels are identified, meaning formerly active riverbeds that have become dry, exactly as on Earth, where formerly connected meanders of the Mississippi are now isolated. Also visible are channels covered with finer sediments, evidence that the river has recently calved, bringing a sediment-laden flow to enrich the delta. The mechanical weathering processes on Titan mainly stem from the force exerted by these moving liquids. Drops of methane or ethane, falling in showers, exert a mechanical erosion action, rounding the surface by repeated abrasion. As the river approaches Ligaea, it deposits its sediment load in areas where the current slows down, particularly at the mouth. There, deltas composed of organic materials and water ice particles are formed, impeded by the meeting with the hydrocarbon sea. Observations of several deposit cycles show that, in Titan's recent history, over thousands or tens of thousands of years, the levels of lakes and hydrocarbon seas have varied. Through seasons and climatic conditions, the region has experienced episodes of heavy rains, profoundly reshaping the landscape, then periods of calm or drought when channels emptied and deltas consolidated. During these drier phases, wind erosion and other mechanisms marked the relief, creating sedimentary layers and dried beds. These phenomena make Titan a natural laboratory where one can follow, step by step, the impact of a methane-based fluvial cycle on an icy surface. To illustrate the fluvial dynamics of Titan compared to the Nile or the Mississippi, it is enough to remember that the fundamental elements are similar. A liquid source, in this case, hydrocarbons, flowing towards a lower area, transporting sediments and depositing them in a receptacle, namely Ligaea. The Nile begins in Central Africa, feeds plains before forming a delta on the Mediterranean. Titan lacks such mountains, but gravity and flow produce a similar outcome. During methane rains, slow-running streams carry sediments over several kilometers or miles before emptying into Ligaea, creating remarkable deltas. With each episode, the delta adjusts and recombines, leaving behind layers of deposit that tell the fluvial history of the Moon. This icy world offers exploration, a unique window into the diversity of solar system fluvial processes. The dendritic networks surrounding Ligaea prove that Titan is not a frozen universe. It lives to the rhythm of hydrocarbon precipitation, flows, and successive deposits, evolving mostly below the freezing point, but according to the same principle. Where a liquid flows, it carries matter, carves the surface, and deposits remnants in a calmer area, gradually sketching characteristic architectures. Deltas are an open book on Titan's hydrological history, tracing the succession of floods and dry periods that have marked its past. Just as the Nile irrigates the Egyptian valley and shapes agriculture since ancient times, and the Mississippi conditions the morphology of the American plains, the rivers of Titan continuously shape the surface of this moon, building and destroying deltas with each oscillation of the levels of hydrocarbon seas. The expression fluvial climate takes on an unprecedented meaning here. The flow, evaporation, and return of methane behave like water on Earth. It's as if we were observing a second Earth, inverted and cooled, where water freezes and methane plays the role of water. The deltaic deposits then become a geological mirror. They retrace the succession of climatic and hydrogeological events, revealing the patient dynamics of nature through time and space. The comparisons with the Nile and the Mississippi are not empty analogies. They constitute a concrete way of sharing with the public an intuitive vision of extraterrestrial rivers. They are not anecdotal, but the proof that beyond Earth, other worlds harbor geological processes capable of sculpting and transforming the surface, testifying to the permanent dynamism of nature. In Ligaea, the fluvial history is written in ice and hydrocarbons, and despite the intense cold, Everything lives there to the patient rhythm of rivers, deltas, and climates that succeed one another in a distant echo of the great terrestrial valleys. The in-depth study of these river networks, their deltas, and this fluvial climate provides essential clues to understand how extraterrestrial environments can be both exotic and familiar. The dendritic channels, products of slow mechanical alteration, testify to erosion by carbon-containing fluids at very low temperatures. Deltaic zones, on the other hand, archive the history of the comings and goings of hydrocarbon seas. The analogies with the Nile or Mississippi help to visualize what a river is on Titan, a fundamental element that wears down the surface and constructs these deltaic structures, reminding us that even under frozen climates, nature shapes its world. In the heart of Titan's high latitudes, the landscape changes radically to reveal liquid expanses similar to miniature seas. With temperatures around 179 degrees or 290 degrees, the notion of an ocean of water seems impossible. Yet, Titan's northern polar regions host vast seas and numerous lakes. Named Kraken, Ligeia, and Punga, these polar seas sometimes reach depths of more than 300 meters or 984 feet. Behind these evocative names, there is a liquid made up of methane, ethane, and dinitrogen, forming an astonishing hydrological cycle that gives Titan the only stable lakes known outside of Earth. To understand these seas, one must mention their discovery during Cassini's flybys. Radar images capable of piercing through the haze revealed vast, smooth surfaces, characteristic of liquid bodies. Kraken Mare, the largest, stretches out like a true ocean, followed by Ligeia Mare and Punga Mare, all located near the North Pole. This choice is not trivial. At the pole, geography and climate favor the conservation of volatile liquids, just as Earth's ice caps do for water. On Titan, the temperature is so low that it solidifies most substances, except methane, which remains liquid, offering a polar landscape both strange and fascinating. In 2024, a radar study from Cornell University, reported by Nature, revealed seasonal waves on the surface of Kraken Mare. Until then, it was thought that weak winds and the viscosity of the mix prevented any notable agitation. These waves, moderate compared to those of Earth's oceans, nevertheless prove the existence of true movement. The winds, even light, generate ripples, while temperature variations change the density of the liquid. When the temperature changes, the solubility of dinitrogen in the mixture evolves, disrupting the balance at the surface and amplifying the action of the wind on these vast expanses. This discovery highlighted the importance of seasonal effects on Titan. In its orbit around Saturn, the Moon undergoes climatic oscillations comparable to Earth's seasons, but over longer durations. When the surface warms by a few degrees, the dissolution of dinitrogen changes, causing variations in the level and composition of the liquid. This can even create dinitrogen bubbles, causing slight fizzing on the surface of Kraken Mare and Ligeia Mare. These clues, although discrete, reveal an unexpected internal dynamism. The Huygens probe provided in situ evidence in 2005. During its descent, it landed in a region suggesting ancient rivers or hydrocarbon showers. Huygens photographed rounded pebbles, made of solid ice but polished by liquid flow. On Earth, such pebbles form in riverbeds where water rounds off stones. On Titan, this mechanical role was played by methane or ethane, revealing an active cycle of precipitation, flow, and sediments. The chemistry of these polar seas arouses great interest. On Earth, water is the main solvent of life and many surface processes. On Titan, water in the form of ice, constitutes the frozen crust, while liquid methane and ethane fulfill the same role as water. Nitrogen, the major gas in the atmosphere, partially dissolves in these seas depending on temperature and pressure. Researchers study these solubility coefficients to understand how bubbles form and how the liquid's density varies across different areas. Fluctuations of nitrogen play a major role in the dynamics of these polar expanses. Another fascinating chemical aspect is the presence of benzene and tholins in these seas. Benzene, on Earth, is a delicate aromatic hydrocarbon, but on Titan, it can precipitate and dissolve in the methane-ethane mix. When the temperature drops, it dissolves, and crystals can appear if it falls further. Tholins are complex organic particles formed in the upper atmosphere under the action of ultraviolet and energetic particles. Falling like a haze, they color Titan a characteristic orange. In the seas, these tholins can settle or dissolve, changing the chemical composition of the beds and shores. Their presence suggests these lakes are the theater of multiple chemical interactions, still poorly understood. In the laboratory, some reactions presumed to occur in these cryogenic environments have been reproduced, showing that precursor molecules of a potentially prebiotic chemistry can form in low-temperature solvents like methane. This chemical complexity also translates into the physical properties of the polar seas. Radar measurements detect reflectivity variations, providing information on the viscosity of the mixture and the presence of dissolved materials. Albedo differences suggest that the seabed is not uniform. There are organic sediments, a kind of hydrocarbon sludge deposited over years, even millennia. On Titan, the low gravity allows these deposits to spread over large areas, while methane cycles facilitate their transport and accumulation. The shores of Kraken Mare raise many questions. Radar images and altimetric data sometimes outline clear contours, like cliffs or steep banks. On Earth, coastal erosion forms beaches, rocky coasts, or sandy deltas. On Titan, sea level variations dictated by the seasonal climate also shape the coastline. Sediment deposits, ice block polishing, and temporary marshy areas are observed. Given the different density of the liquid, waves do not behave the same way as on Earth. They do not break on the beach, but can erode the coastline in an unprecedented way. Another mystery concerns the depth of these seas. Estimates suggest up to 300 meters or 984 feet for Kraken Mare, but they rely on the interpretation of radar signals passing through the liquid. To obtain more accurate measurements, the exact chemical composition must be considered. The more loaded the liquid, the more it absorbs energy from the signal, skewing the estimated depth. Future missions, like the Talise submarine concept, could directly explore these depths. Such craft would offer an unprecedented view of the liquid layers and solid deposits. Imagining strata of tholins accumulated over millions of years or traces of past climatic variations already excites planetologists. Understanding the chemistry of these lakes is also crucial for assessing the possibility of life, even rudimentary, in these extreme conditions. Without oxygen or liquid water, terrestrial life seems unlikely, but some protocols suggest that exotic reactions fueled by liquid methane and ethane, perhaps catalyzed by tholins, could occur. Testing these hypotheses will require new instruments capable of sampling the liquid at different depths and analyzing the seabed. Existing data already inspire mission projects, sometimes at the idea stage, that could reveal mechanisms of organic molecule formation still unsuspected in this cryogenic environment. Today, as we scrutinize the radar echoes more closely and compare our maps of the polar seas to those of a terrestrial shoreline, Titan fuels the hope of major discoveries. Each new observation, whether of detected waves or a surprising deposit, refines our understanding of the unstable balance reigning in these hydrocarbon lakes. Little by little, the image of an inert satellite fades to reveal a magnificent extraterrestrial expanse, both familiar due to the liquid aspect and profoundly surprising because of its composition. Step by step, the knowledge gained about Kraken Mare, Ligeia Mare, and Punga Mare extends our fascination with extraterrestrial chemistry. The adventure is just beginning. Future missions better equipped to probe these expanses could transform our vision of what an ocean beyond Earth could be. And what if, one day, diving into a polar lake on Titan became a reality? We could then admire those icy pebbles, those fleeting waves, and the orangish mist from the surface of this distant world, where meteorology and geology defy all our reference points. Titan's polar seas and lakes are a realm of exploration at the frontier of science and imagination, witnessing a fascinating chapter yet to be written in the history of this enchanting moon. Across Titan's vast landscape, the equatorial region is distinguished by immense dune fields stretching over more than 100 kilometers or 62 miles, oriented from west to east. These forms, spectacular in their regularity, sometimes reach 100 meters or 328 feet in height and evoke terrestrial sand dunes. But detailed observations reveal a very different world where organic chemistry and extreme conditions transform each grain into an almost exotic object. According to a reanalysis of Cassini data published in 2023, the composition of these dunes is more complex. The grains are not simple minerals, but organic molecules covered with a thin ice layer containing hydrogen, carbon, and nitrogen. At these temperatures, this ice acts as a binder, encasing the particles and giving them the cohesion necessary to form immense chains of dunes, despite the low gravity and high atmospheric density. This discovery revolutionizes our understanding of the circulation of organic materials on Titan's surface and provokes interest in future missions. The shaping of these dunes largely depends on katabatic winds, cold currents descending from highlands to low areas under the effect of gravity. On Titan, these winds are modulated not only by temperature differences between the surface and air at altitude, but also by gravitational tides caused by Saturn. As Titan orbits the gas giant, this pull varies and influences the dominant wind direction. The dunes thus form a complex dance between Saturn's attraction and Titan's atmospheric dynamics, creating these dune landscapes Cassini immortalized, which continue to fascinate research. Imagine a pale horizon merging into a cold, dense atmosphere. Unexpected reliefs rise on the surface, composing a landscape frozen in ice. Yet, beneath this apparent stillness, geological processes silently shape the grounds and mountains of a distant world, Titan. Among its most striking formations, the Methane Mountains, 3 kilometers or 2 miles high, and the domes of Sotra Patera, possible witnesses to cryovolcanism mixing water and ammonia. These phenomena could contribute to the renewal of methane present in the atmosphere. To understand them, we must explore the formation of Titan's reliefs, where tectonics and cold volcanism combine. Tectonics refers to the deformations of the crust of a celestial body under the effect of internal tensions. On Earth, it results from the movement of large plates. On Titan, the icy crust, made of water and various elements, can fracture under the pressure of internal forces, such as cooling or the presence of deep liquids. Signs of surface extension appear in certain areas. The Mithrim Mountains illustrate this dynamic, reaching a surprising height for a satellite with a light crust and low gravity. To understand their formation, imagine the crust as a stack of icy layers, rigid at the surface, more malleable in depth. Under the influence of uplifts linked to Saturn's tides or internal heat, blocks can crack and rise. In some regions, this causes a progressive stacking of blocks, creating reliefs. Radar data suggests a slow uplift associated with crustal extension. Pieces stretch, overlap, and form a narrow, elongated chain. The height of these mountains is explained by Titan's low gravity, which allows large structures to exist without collapsing. The ice, enriched with ammonia, can also become more rigid at very low temperatures, which favors the stability of significant reliefs. These properties give the massifs an unusual solidity in such a glacial environment. But beyond tectonics, Titan shows even stranger structures, cryovolcanoes. These volcanoes emit not lava, but a frozen fluid composed of water, ammonia, and other volatiles. On Titan, where extreme cold reigns, the idea of a volcano spewing water instead of molten rock seems improbable. Yet images from probes support their existence. The Sotra Patera domes are the most notable. These structures, with rounded shapes and sometimes hollowed tops, measure several dozens of kilometers or miles. Their appearance evokes collapsed craters. According to researchers, a warmer layer beneath the ice could, under pressure, make a mixture of water and ammonia rise. Upon reaching the surface, the drop in pressure would cause a fluid ejection, creating depressions and forming domes at the edges of these icy vents. Ammonia plays a central role here. It lowers the freezing point of water, allowing a liquid to persist despite the 170 degrees or 274 degrees on the surface. This fluid could rise through cracks, deposit ice, or carve out underground channels. It's a phenomenon very different from terrestrial volcanism, but based on the same principle. A warmer material rises and spreads at the surface. The domes could also play a role in maintaining atmospheric methane. Titan possesses an astonishing amount, even though this gas should quickly disappear under radiation effects. This fact implies the existence of an internal mechanism capable of regenerating the supply. Cryovolcanism could be the source. Eruptions could release methane trapped in the depths or dissolved in fluids. Sotra Patera might then act as a valve to maintain this atmosphere. But the evidence remains incomplete. The dome morphology does suggest fluid upwellings, but heat emissions or recent deposits are not always visible. Cryovolcanism could thus be ancient, sporadic, or have had a more active past. In any case, these structures indicate internal activity capable of injecting methane through the crust. The environment of Sotra Patera offers additional clues. Its slopes seem little eroded, suggesting a relatively recent formation. On Titan's scale, this could mean a few tens of millions of years. Collapses, fractures, and deposits reinforce this idea. A fluid might have erupted, forming a dome before the central area collapsed, similar to terrestrial calderas. Simultaneously, the formation of the Mithrim Mountains in Sotra Patera could be linked to Saturn's tides. Titan, subjected to these forces, experiences internal friction that generates heat. This local warming can melt the ice and create pockets of water. When they become unstable, these pockets pierce the crust, leading to episodes of cryovolcanism. This cycle links gravitational forces to the restructuring of the surface. The extensional tectonics and cold volcanism also raise the question of the presence of an underground ocean. If a liquid layer exists beneath the ice, it could explain the upwelling of materials. The thickness of the crust is crucial here. The thinner it is, the more easily fluids can circulate. The mountains indicate that the crust might be variable, giving way under certain constraints to allow water to pass. To measure the impact of these phenomena on Titan's evolution, scientists analyze the local compositions. If the upwelling of water ice is confirmed, the role of cryovolcanism in supplying the atmosphere becomes clearer. Each cold eruption could release methane trapped in hydrates, these crystalline structures that store gas. Even a slight temperature rise makes them unstable, releasing methane to the surface and then into the air. The scientific community agrees on the existence of past tectonic and volcanic activity. However, their frequency and intensity remain uncertain. Titan may experience periods of activity interspersed with long silences. The Mithrim Mountains, although immobile today, testify to a slow but massive uplift. They are the result of an extensive process of ice accumulation, modest on a terrestrial scale, but impressive for an ice world. The Sotra Patera domes, on the other hand, embody another expression of this dynamic, that of liquid eruptions. The word patera refers to depressions surrounded by rims, signs of volcanic activity. Their altitudes vary dramatically, sometimes by several hundred meters or about 1,000 feet, and their slopes are steep. This morphology is not solely explained by tectonics. Few summits on Titan exhibit such contrasts, reinforcing the idea of active or recent volcanism. By cross-referencing topographic data with possible gravity or temperature anomalies, we could detect signs of underground flows. On Earth, these methods already allow us to identify volcanic activity. On Titan, despite the thick atmosphere and distance, probes have provided valuable clues. Water and ammonia volcanism place Titan alongside Europa and Enceladus as one of the few bodies in the solar system still geologically active under the ice. This duality highlights a key question, the replenishment of methane. Without cryovolcanism, methane should disappear. Titan's atmosphere is slowly transformed by radiation, generating complex organic particles. This process forms its famous orange haze, but its persistence implies regular inputs. Occasional eruptions would suffice to sustain this cycle, injecting methane into the air and fostering weather based not on water, but on hydrocarbons. This cycle relies on the interaction between internal forces and the atmosphere. The Mithrim Mountains embody Titan's tectonic momentum. The Sotra Patera domes represent the silent explosion of glacial volcanism. Together, they demonstrate this moon's capacity to repair, transform, and adapt, intermittently releasing a breath of methane into a veiled sky. These landforms are therefore not frozen. They tell the story of a world in perpetual renewal. The Mithrim Mountains mark the imprint of an ancient uplift. The Sotra Patera domes breathe the memory of cold eruptions, capable of reshaping the ground and releasing methane. Even in the icy darkness of the solar system, Titan shows that a world can remain active, influence its atmosphere, and hint at an unsuspected complexity beneath its surface. The periodicity of this cryovolcanism remains to be elucidated, but the evidence converges. Titan is not a dead body. The studied reliefs prove that it possesses its own activity, guided by a frozen heart capable of awakening at regular intervals. This water and ammonia volcanism might very well be the key to maintaining its atmosphere, and thus its identity. This is the essence of these icy peaks and domes. To illuminate how these structures form, reveal the role of domes in the methane cycle, and understand why Titan, so distant, offers a unique glimpse into low-temperature geological processes. It is a moon where ice takes the place of rock, where water becomes lava, and where the frozen reliefs conceal one of the cosmos's most captivating dynamics. The 13th stage of our journey around Titan, the exploration of its internal ocean and deep structure, immerses us in an unknown and fascinating geology. To grasp the significance of this layer hidden beneath the ice, we must return to the observations of the Cassini probe, which explored Saturn and its moons for more than a decade. Thanks to its gravimetric sensors, capable of measuring variations in the gravitational field, scientists highlighted a discrepancy unexplained by a simple accumulation of ice. It was then supposed that a denser layer of liquid water existed deep down. This discovery changed our understanding of Titan's internal workings. Despite extreme cold, a subterranean ocean, comparable to Earth's salt lakes, appears to spread beneath the crust. The gravimetric measurements were compared to altimetric data, confirming the presence of a salty ocean under an ice layer of 55 to 80 kilometers or 34 to 50 miles thick. As a comparison, Earth's crust reaches dozens of kilometers or miles depending on the regions. On Titan, this ice thickness overlays a global liquid reservoir, making this moon similar to other oceanic worlds like Europa or Enceladus. Local gravity reveals the density of materials. Saltwater is denser than ice. When measurements reveal anomalies, it indicates the presence of heavier layers, like a salty ocean. The dissolved salt enhances this density and suggests that Titan is structured like a small, differentiated planet with distinct internal layers. Seismological studies published in 2024 reinforced this hypothesis. By analyzing surface waves caused by earthquakes or impacts, researchers modeled the propagation of vibrations through the crust. The results indicate a thickness of approximately 50 kilometers or 31 miles, with a 10 kilometer or 6 mile uncertainty. The average density of the ice is estimated at 925 kilograms per cubic meter or 58 pounds per cubic foot, consistent with impure ice, enriched with nitrogen or organic compounds. The internal structure also depends on residual heat. Titan retains energy from radioactive decay and tidal forces exerted by Saturn. These forces create friction that warms the interior, keeping part of the water in a liquid state. However, the ocean remains very cold, a few degrees above freezing. Dissolved salts lower this point, facilitating the presence of water despite the freezing environment. Another key element, methane clathrates. These are structures where gas is trapped in ice cages. On Titan, methane, a major gas after nitrogen, fuels an active meteorological cycle. According to a recent hypothesis, part of the methane could be stored as clathrates in the crust. When they break or warm, they release the gas, enriching the atmosphere. Conversely, if conditions become colder, methane becomes more durably trapped. These reservoirs would explain the persistent presence of this gas, despite its natural decomposition. For these clathrates to exist, temperature and pressure must be suitable. The pressure due to the ice and the low temperature favor their formation. Convection in the ocean, although slow, plays a role. Differences in density or temperature cause slight water movements, influencing methane stability. Even at a very slow pace, this circulation contributes to the balance between ocean and crust. In the long term, Titan could lose its internal heat. If tidal forces decrease, the ice will thicken, and the ocean will eventually freeze. Without an ocean, the methane cycle will slow significantly, impoverishing the atmosphere. Titan would then resemble Pluto, an icy surface, a frozen structure, and a thin atmosphere. It would be the end of an active cycle that maintained rains, lakes, and mists. This evolution will not occur for billions of years, but it highlights the importance of studying Titan today. Each discovery sheds light on the complexity of icy moons. Titan is not an inert block, but a world in transformation, where geology and chemistry are intimately intertwined. Studies specify that the ocean contains sodium salts, magnesium, and a bit of ammonia, which remains soluble at low temperature. The interface between the ocean and the crust could harbor clathrates, creating a natural barrier. Exchanges of methane with the surface could occur through fractures or conduits, contributing to the atmospheric cycle. The question of prebiotic chemistry has intrigued scientists. On Earth, water, salts, and geothermal energy are essential to life. Titan offers some of these ingredients, although the environment there is vastly different. The temperature, lack of oxygen, and other limitations make this scenario speculative, but the very existence of an ocean makes it a crucial object of study. Future missions could break through this crust or deploy instruments capable of listening to the depths. The data from Cassini remain fundamental, yet many mysteries persist, especially concerning the links between ocean and atmosphere. If one day the ocean were to freeze, Titan would lose its internal engine. Storms, methane rains, and shifting landscapes would disappear. The world would become inert, perhaps with a thin residual gas layer, but without current activity. For now, Titan is a unique natural laboratory. Its deep ocean, trapped beneath ice, is a key to its dynamics. Each mission reinforces the idea that this moon is far more than a frozen celestial body. It is a complex, animated world where ice, salt, methane, and slowness combine to form a universe in constant transformation. The 14th step of our journey through the system of the ringed giant. Focus on Titan's organic chemistry, complex and fascinating. We are going to explore the recently discovered chemical reactions, the formation of co-crystals in the lab, biomass estimates, and clues guiding the search for biosignatures. Titan is a moon rich in carbon molecules, essential to the chemistry of life. But its oxygen-free atmosphere produces reactions foreign to our world. It is in this context that the question of life on Titan takes on its full dimension. In 2025, researchers highlighted in the laboratory reactions between two families of molecules, alkynes and nitriles. Alkynes feature a triple bond between two carbon atoms. Nitriles, on the other hand, have a cyano group with a triple bond between carbon and nitrogen. These molecules abound on Titan, formed in the atmosphere by the action of solar and cosmic radiation. Experiments were conducted with propionitrile and acetylene, placed in a simulated Titan atmosphere at very low temperatures and under controlled pressure. These conditions allowed for the formation of co-crystals, structures where the two molecules assemble without merging. This phenomenon shows that unprecedented molecular interactions are possible on Titan. These co-crystals could trap, transport, or release organic matter to the surface or in the atmosphere. This discovery is crucial. It reveals chemical pathways that, in theory, could produce substrates usable by a form of life. On Earth, life relies on liquid water, energy, nitrogen, and organic molecules. On Titan, Water seems absent on the surface, but seas of hydrocarbons and a nitrogen-rich atmosphere favor the formation of new molecules. The chemistry observed at 180 degrees and 292 degrees fuels a daring hypothesis. Could a life form independent of water and oxygen exist here? But a study published in 2025 tempered this enthusiasm. It attempted to evaluate the theoretical biomass possible on Titan. Considering the available energy, the slowness of reactions, and the efficiency of biological processes, researchers estimate that the biomass would not exceed a few kilos, around a few pounds, spread over the entire surface. A possible life, but very sparse, slow, and difficult to detect. On Earth, dioxygen allows for high energy production. On Titan, potential life forms would have to settle for less powerful reactions, involving hydrogen or nitrogen compounds. These low yields, coupled with the extreme cold, would greatly slow down metabolisms. Even if a form of life exists, it would be very limited, perhaps imperceptible. Yet the existence of microorganisms based on unknown biochemistry cannot be ruled out. Researchers are therefore interested in biosignatures. These are signs of biological activity, like an imbalance in the proportions of certain compounds. On Titan, an excess of methane compared to ethane, or an abnormal ratio between carbon-12 and carbon-13 isotopes, could betray the presence of metabolism. Methane is mostly gaseous, ethane liquid. These two molecules can exist without life, but unexpected proportions would warrant an in-depth investigation. Isotopic analysis completes this work. On Earth, life prefers carbon-12. An anomaly in favor of this isotope could signal biological activity. On Titan, such an imbalance would be a strong indicator, but difficult to distinguish from a simple chemical process. Several signals would need to be corroborated: scarcity of certain molecules, methane excess, atypical isotopic profile. Together, these elements could justify targeted exploration. Despite the extreme conditions, Titan's organic chemistry is unusually rich. Co-crystals containing carbon and nitrogen are a good example of this complexity. They could one day serve as a basis for unknown biological functions. Although abundant life seems unlikely, these results push the boundaries of our understanding of prebiotic chemistry in the universe. These processes not only serve the search for life, they also help to better understand the chemical evolution of Titan. Methane is regularly destroyed there, yet remains abundant. If geological or photochemical processes are insufficient to regenerate it, an unknown source, chemical or biological, might be involved. The chemical puzzle of Titan remains incomplete, but each new piece reveals a bit more. Titan's organic chemistry reminds us that life could emerge without water or oxygen. Even if the estimated biomass is low, this moon remains a precious natural laboratory for understanding prebiotic scenarios. The observed co-crystals show that reactions are possible at very low temperatures. Chemical imbalances might one day signal living activity. We are only at the beginning, but Titan already reveals surprisingly dynamic chemistry. Who knows if, somewhere in this orange world, a spark of life awaits discovery. In the early 1980s, modern exploration of Titan begins. Voyager 1, launched by NASA, flies by Saturn and its moons. Initially dedicated to Jupiter, the mission is extended to Saturn with a clear objective: to graze Titan. In November 1980, the probe measures for the first time the temperature of Titan's upper atmosphere, close to 180 degrees or 292 degrees. The instruments, although advanced for the time, are limited. The images remain blurry, obscured by an orange haze. Yet, this dense and cold atmosphere intrigues. Why such a gaseous envelope on this moon? After this flyby, Titan becomes a subject of growing interest. Data from Voyager 1 reveal complex organic chemistry, rich in carbon and nitrogen. Over the years, the idea of a dedicated mission becomes imperative. In collaboration with Europe, NASA designs a far more ambitious exploration, the Cassini-Huygens mission, intended to unravel the mysteries of Saturn and its numerous moons, especially Titan. Cassini, launched in 1997, will take 7 years to reach Saturn. It carries a European module, Huygens, intended to land on Titan. Named in honor of 2 great astronomers, these crafts are set to make history. Cassini arrives in 2004. Huygens is deployed a few months later. Thus begins a decade of unprecedented exploration. Between 2004 and 2017, Cassini performs 127 flybys of Titan. It observes the moon from all angles, at all altitudes, across seasons. It collects 350 gigabytes of data on Titan's chemistry, geology, atmosphere, and magnetic fields. Far more than a simple flyby, it's an extended immersion into an unknown world. Cassini deploys all its instruments, radars to map the surface, infrared spectrometers, high-resolution cameras, particle sensors. The highlight remains January 14, 2005, when Huygens begins its descent into Titan's atmosphere. Protected by a shield and slowed by parachutes, the lander passes through layers of gas, recording pressure, temperature, winds, and chemistry. It lands at 179 degrees or 290 decimals on a plain of ice pebbles, possibly shaped by hydrocarbon liquids. These data change our perspective on icy worlds. The landing was just one facet of the achievement. For 13 years, Cassini observes Titan at all latitudes, through the seasons. This period equates to half of a Saturnian year. It allows for studying clouds, storms, and meteorological cycles above methane seas. These observations shake our understanding of extraterrestrial atmospheres. But what left a lasting impression was the sound. In January 2005, Huygens recorded the whisper of the wind on Titan through its sensors and microphones. After processing, this faint noise was broadcasted on Earth. The BBC relayed the recording, offering the public an unprecedented sensory immersion, hearing the wind of another world over 1 billion kilometers or 621 million miles away. This moment of emotion made the mission even more memorable. It proved that a craft could land, withstand extreme conditions, transmit data, and offer a window into a distant world. Huygens inspired new projects, flying drones, submarines to explore Titan's seas, and floating devices capable of mapping the surface. In September 2017, Cassini concluded its mission with a final plunge into Saturn's atmosphere, avoiding contamination of moons like Enceladus or Titan. This grand finale does not mark an end. The collected data continues to fuel research, continuously revealing new details about Titan and its environment. Cassini-Huygens is also a success of cooperation. NASA, ESO, the Italian agency, and other partners joined forces for this complex mission. The shared expertise and resources enabled an exemplary exploration, celebrated worldwide. When we think back to Voyager 1, with its blurry images and initial measurements, we see how far we've come. Cassini mapped Titan, identified its lakes, tracked its clouds, and analyzed its atmosphere. It also explored Saturn, its rings and other moons. A decade of science for a renewed understanding. Titan is no longer an orange blotch, but a complete world with its climate, landscapes, and even its soundscape. Voyager paved the way. Cassini-Huygens delved deeper. Their work, spanning over 30 years, allowed us to follow Titan for half of its long year. We saw it change. We listened to it. The legacy is immense. The archives from Voyager 1 are still used, just like the hundreds of gigabytes from Cassini. They fuel future projects, drones, submarines, specialized orbiters. Everything stems from the discoveries of these two missions. And then there is that unforgettable anecdote, the wind of Titan, heard on Earth thanks to Huygens. This breath from elsewhere touched millions of people. More than a scientific feat, it was a bridge between worlds, a proof that space exploration, beyond numbers, also speaks to our imagination. Sixteenth step of our imaginary journey to the heart of Titan, Saturn's largest moon. Today we explore the most recent discoveries and the big questions they raise for future research. At this stage of our cosmic epic, we are at the junction between technological advances and scientific curiosity. Titan continues to reveal its secrets, thanks to ever more precise instruments. We will see the latest data from the James Webb Space Telescope, the meteorological mechanisms of this moon, the anomalies related to methane, and the potential role of certain molecules in prebiotic chemistry. Let's dive together into these fascinating revelations. First major announcement. The James Webb Space Telescope has detected clouds, a sign of the return of spring in the northern hemisphere. Titan's seasons last much longer than those on Earth due to Saturn's extended orbit around the Sun. The transition from winter to spring takes several years. The recently captured images show a gradual awakening of the moon with the appearance of wispy clouds in areas now more exposed to sunlight. These observations confirm the models of specialists who were anticipating this seasonal return. But how do we observe clouds so far away? Thanks to infrared, we can discern variations in temperature and atmospheric composition. Titan is rich in nitrogen and methane, two essential components for cloud formation. James Webb analyzes their light signature to deduce their altitude and evolution. This activity confirms the existence of a slow but real climate cycle, where meteorological phenomena intensify with the increase of solar energy, even though it is very weak compared to Earth. Scientists are also looking into an associated phenomenon, convection in polar lakes. These lakes, filled with liquid hydrocarbons, could be driven by internal movements triggered by gradual warming. Like on Earth, a layer of warmer liquid rises while a colder one sinks. These currents could create a mini internal circulation in these seas of methane and ethane, altering the behavior of the local atmosphere. This internal circulation could fuel clouds and even cause storms. Titan's dense air and extreme temperatures allow methane and ethane to remain liquid. Vapor-laden air masses rise, forming storms with actual hydrocarbon downpours. Very different from our rains, these precipitations indicate an active meteorological cycle. Thus, the convection of the lakes sheds light on the complex chemical and climatic dynamics of Titan. Another mystery persists. Why doesn't the quantity of methane decrease as expected? In theory, this molecule should degrade under solar radiation in a few tens of millions of years. Yet, Titan still contains a large amount of it. This observation suggests a continuous and still unknown source of methane. Several theories have been proposed. Underground reservoirs might be releasing stored methane from icy traps. A form of cryovolcanism, with ice enriched in chemical compounds, could also be responsible. Others suggest a mysterious underground chemistry that transforms organic elements into methane. Although the exact mechanism is still unknown, the persistence of methane fuels interest in this decidedly very active moon. Meanwhile, a discovery about nitriles draws attention. An abnormal abundance of nitrogen-15 has been detected in these organic molecules. Nitriles, composed of carbon and nitrogen, are crucial for prebiotic chemistry. Nitrogen-15 is a heavier version than nitrogen-14. This isotopic disproportion could alter the rate or nature of chemical reactions. It intrigues researchers with its implications for the origins of organic chemistry. These nitriles could form more complex molecules, precursors to life's components. On Earth, certain simple molecules can evolve into organized structures under favorable conditions. Titan, though very different, could host comparable reactions. Its atmosphere rich in organic molecules and its hydrocarbon lakes make it a natural laboratory for primitive chemistry. The role of nitrogen-15 remains uncertain. Some see it as a factor for chemical stability at low temperatures. Others think it results from a natural fractionation inherited from Titan's past. Whatever the origin, the concentration of nitrogen-15 raises questions about its influence on the overall chemistry of this moon. Could it trigger prebiotic reactions? Can its formation be observed directly? In this context, the notion of chemical imbalance becomes essential. On Earth, life modifies the atmosphere by producing and consuming gases. On Titan, an imbalance in the ratio of certain compounds could betray a novel geological or chemical process, or even a biological phenomenon. The idea that an unusual assembly of molecules and isotopes signals unexplained activity fascinates astrobiologists. Even without proof of life, the observed chemical complexity is enough to motivate exploration. These discoveries thus offer multiple perspectives. The clouds indicate a climatic cycle, methane remains a mystery, and nitrogen-15 enriched nitriles pave the way to prebiotic scenarios. Titan becomes a unique model of chemical evolution in an extreme environment. By gradually revealing its secrets, Titan only reinforces its status as a crucial object of study. The diversity of its phenomena, from clouds to convection, from persistent methane to unusual nitriles, challenges our classic frameworks. This moon acts as a natural laboratory, where processes invisible elsewhere suddenly become observable. And as future missions, drones, or submersibles prepare to go further, we are likely on the brink of even deeper discoveries. Here is the current portrait of Titan. This satellite, once perceived as a silent, icy ball, is becoming a complex world, oscillating between familiarity and strangeness. Seasons, storms, chemical balances, and promises of prebiotic chemistry intermingle there. Titan could hold major clues about the origin of molecular complexity in the universe. an infinite field of exploration, ready to reveal its secrets to those who approach it with the right tools and questions. The future of exploring Titan is increasingly captivating. The Dragonfly project, planned for a launch in July 2028 and an arrival in 2036, promises to be one of the boldest missions ever conceived. It aims to transform our understanding of this moon of Saturn. Its originality lies in an autonomous device capable of covering long distances to analyze various sites, offering an unprecedented global view of Titan's geology and chemistry. Dragonfly is a helicopter powered by a radioisotope thermoelectric generator. This system converts heat from radioactive decay into electricity, ensuring a constant energy source despite very low sunlight and extreme temperatures. This energy autonomy allows the craft to operate sustainably under Titan's dark sky. Thanks to Titan's dense atmosphere, 4 times that of Earth's, flight is facilitated despite lower gravity. Dragonfly is equipped with contra-rotating rotors to ensure stability and lift. It will be able to take off, move, and land vertically, aiming for at least 175 kilometers or 109 miles of cumulative flight. This distance will allow exploration of a diversity of terrains, plains rich in organic compounds, vast parallel dunes, and edges of hydrocarbon lakes. The mission will first target the equatorial region of Shangri-La, known for its chemical richness. These dark dunes, formed by atmospheric deposits, could illuminate prebiotic chemistry linked to the origins of life. Among the onboard instruments, the mass spectrometer will precisely identify the encountered molecules. By ionizing samples, it will reveal their chemical and isotopic composition. Dragonfly could also be equipped with a sampling device to analyze the soil in depth, as well as high-resolution cameras and environmental sensors. The mission will also study Titan's internal structure. Seismic sensors will try to detect possible moonquakes. The analysis of seismic waves could reveal the existence of a subsurface ocean of water and ammonia, and detail the exchanges between this liquid reservoir and the atmosphere. Dragonfly is part of the quest for the origins of life. With its dense atmosphere and active geology, Titan is a natural laboratory for exobiology. The mission will try to solve several mysteries: the formation of aerosols, the composition of dunes, the balance of organic gases, and the possible presence of niches conducive to primitive life. Other projects could complement this mission. Talise, a submarine designed to navigate Titan's hydrocarbon seas, aims to map the bottoms, analyze the chemistry of the lakes, and collect sediments. This project, still theoretical, faces major technical challenges, notably the resistance of materials in cryogenic liquids. Another concept, still under study, proposes a high-resolution radar orbiter. Between 2004 and 2017, the Cassini probe mapped 2/3 of Titan. A new orbiter would provide more detailed images and track dynamic phenomena like the seasonal variations of lakes or the appearance of rivers. Dragonfly ushers in a new era for Titan exploration. This flying laboratory will be able to explore areas inaccessible to rovers, linking several sites to reconstruct the geological history of a broader region. Flights over the dunes of Shangri-La promise unprecedented data. Initially, the mission plans for a few years of exploration, But if Dragonfly exceeds expectations, it could extend its mission, much like many Martian rovers. The collected data will allow the study of prebiotic chemistry and perhaps the detection of traces of primitive life. On a technical level, Dragonfly illustrates the union of innovation and adaptability. Its rotors ensure agility. The nuclear generator provides continuous power. Navigation will rely on proven techniques, with stereo imaging, laser altimetry, and trajectory calculations. It also includes a seismic element to probe the depths. When Dragonfly completes its mission, it will leave behind a treasure trove of data. These archives will fuel research for decades and inspire new projects. Talise and the radar orbiter could follow to complete Titan's mapping. Scientists are already questioning the origin of the methane, the formation of organic deposits, and potential cryovolcanic activity. The officialization of Dragonfly marks a crucial step. It shows that with perseverance and ingenuity, we can aim for distant worlds to bring back revolutionary knowledge. Dragonfly also relies on broad cooperation between agencies, laboratories, and companies. The technical challenges are immense. Engineers must contend with extreme cold. Scientists define targets and strategies. Chemists hope for revealing samples. All unite their efforts towards a common goal. Its long journey to Titan, beginning in 2028 for an arrival in 2036, gives the scientific community time to refine every step. Crossing space, arriving in the atmosphere, and then autonomous flight on Titan are all trials that will demonstrate how far humanity can go. We already imagine the images Dragonfly will transmit: vast dunes, mists laden with organic molecules, shimmering lakes, strange reliefs. Each detail will provide clues about Titan's geochemical history. The public will follow this journey, thanks to transmissions relayed from Saturn. After Dragonfly, other missions should follow. A submarine would explore the hydrocarbon seas. A radar orbiter would observe the seasons and terrain changes. Little by little, Titan will be revealed, from its frozen core to its misty atmosphere. And always, the central question: can Titan harbor life? The future of Titan exploration looks exciting. Dragonfly revives a saga that began decades ago with the first probes. Today, flybys and flying devices are taking over. Thanks to the nuclear helicopter and complementary projects, Titan may soon have no secrets, and perhaps one day, an astronaut will walk on its mysterious dunes.